In this video, I'm going to be talking about some geometric applications of antichains. This is work with my advisor, Cyril Harpoled, and is a talk for the Canadian Conference on Computational Geometry. So let me just dive right into what I'm going to be talking about today, and to do so, I'm going to provide some refreshers. So we're going to be working with partially ordered sets, and below I just have an example of a partially ordered set where the arrows correspond to comparability of elements. And recall that a chain is a subset of elements such that every pair of elements in the set are comparable. So in the figure below, these four blue elements are a set of elements which are comparable. Perhaps unsurprisingly, an antichain is a subset of elements in which all pairs are incomparable. So again, in this figure below, I've highlighted three elements which are marked red, which form an antichain. We can also define something known as a chain cover, which is a collection of chains covering the elements. So in this picture here, I've drawn three chains which cover the elements of V. And it's well known that the largest antichain is equal to the smallest collection of chain covers. And this has been known since the 1950s and proved by Dilworth. And these days you can also prove it via max-flow min-cut. Today, this talk is really going to be focusing on implicitly defined posets. So what I mean by this is posets where the elements are underlying geometric objects, usually of constant description complexity, and you can efficiently test whether two elements are comparable according to the poset you define. So for example, here I have a point set P, and I can define a poset where I say P is less than Q if P dominates Q. And remember, domination is for each coordinate I, Pi is greater than or equal to Qi. And in the figure below, I've just given an example of 2 points P and Q such that P dominates Q. And really what we're interested in this talk is antichains, and what does a specific antichain correspond to after defining the poset? Well, in this case, an antichain corresponds to a downward staircase of points. Specifically, we define them in this talk as a Pareto-optimal subset. So in this figure, these 7 points here form a downward staircase or a Pareto-optimal subset. And so really in this talk, we're going to be asking ourselves, how quickly can we find the largest Pareto-optimal subset? In 2 dimensions, you could do it in n log n time, but I'm also interested in the high dimensional version of the problem. And so we'll see that computing the largest Pareto-optimal subset reduces to computing the largest antichain in this poset. Here's a second example of implicit posets. Let's say D is a collection of regions in R to the D. And I can define a poset where I say two regions, D prime and D. D prime is less than D if D is fully contained in the interior of D prime. So in the figure below, I just have an example of two elements like D and D prime. And so what is an antichain in this poset? This corresponds to a subset such that for every two regions, D1 and D2, D1 is not contained in D2, and D2 is not contained in D1. And we call such a subset a loose subset. So in this figure below, the highlighted red elements form a loose subset. Notice that the elements are allowed to be intersecting. Again, they just cannot contain one another. And so again, how quickly can we find the largest loose subset? Or equivalently, how quickly can we compute the largest antichain in this poset I've defined? So in terms of computing antichains, combinatorially speaking, the largest antichain on a poset of n elements can be found in n to the 2.5 time. How does this algorithm work? Well, you essentially reduce the computation to finding a maximum matching in some bipartite graph G, which you can define, and then recall that the Hopcroft-Karp algorithm can compute the maximum matching in a bipartite graph G in n to the 2.5 time. And from this maximum matching, you can extract an antichain and also a chain cover, which have the same size by Dilworth's theorem. But here, of course, we're dealing with implicitly defined posets. So, of course, one way to run the algorithm is construct this bipartite graph, and all of the edges of the graphs correspond to comparability between certain pairs of elements, and we can just construct the graph explicitly. But since we have implicit posets, we want to kind of run this max matching algorithm of Hopcroft and Karp implicitly on the graph G, right? Which is also implicitly defined because we have this implicit poset. So we're looking for any sort of speed up we have here in order to exploit the fact that our poset is implicitly defined. So the framework which we present in this paper is the following algorithmic framework for implicit posets. So just recall, we have our poset V of size n, and our goal is to compute the largest anti-chain for V. So to do so, we're going to assume that we have access to a data structure. So for any subset of elements P of size M, we assume we have a data structure which acts on those subset of elements P that can do the following three operations. It can perform a query operation, which, given an element in V, returns an element U in P, such that V is less than U. Okay, and this has to run in Tm time for some function T. The second requirement is that we are able to delete an element from the data structure in Tm time. And the third requirement is that we can construct this data structure in mTm time. Okay, so we're essentially only requiring that this data structure is semi-dynamic. We don't need insertion of elements. We just need to be able to construct it and then delete elements. But if we have a data structure with these requirements, then we can show that you can find the largest anti-chain for V in n to the 1.5 Tn time. Now, some just remarks about this theorem of ours is that the idea is, like I mentioned, to simulate the Hopcroft-Karp algorithm implicitly on this bipartite graph using the data structure and querying the data structure appropriately to find out the edges of the graph. This is actually based on a framework of Efrit et al. In 2001, and there they were interested in computing the largest bottleneck matching in a given graph. So it's very similar to our approach, but we're coming at it from the angle of anti-chains. And recently, there's also been another similar framework proposed by Cabello and Meltzer, where they look at computing minimum cuts in disk graphs. And again, you're looking at these geometric graphs which are implicitly defined, and they use geometric data structures to speed up these minimum cut algorithms. So it's a very similar framework to ours. In the rest of the remaining time, I'm going to talk about applications of this anti-chain framework we developed. So let's go back to the largest Pareto-optimal subset problem. So recall that we're given a point set P, and we say that for 2 points P and Q, P dominates Q if each coordinate of P, for example, Pi, is greater than or equal to Qi for all I. And we say a subset Q is Pareto-optimal if no point in Q dominates any other point in Q. Okay, and so remember, in the context of anti-chains, or rather posets, a subset Q which is Pareto-optimal is exactly an anti-chain in the poset for P. So we want to compute the largest anti-chain in this poset. And to do so, we need to exhibit a data structure which can perform those three operations I mentioned earlier, namely querying, deletion, and construction. Querying is probably the most difficult part of the three, so I'm just going to focus on that. So what do we need? We need a data structure which can perform the following query. Given a point V, the data structure must return a point U such that V is less than U. Now, in the context of our poset, this is exactly the same thing as asking, given an element V, we want to return an element U such that U is dominating V. So you can check that U dominates V if and only if U lies in the following D-sided box, right? So this is hold since we're requiring that each coordinate Ui is greater than or equal to the corresponding coordinate Vi, and that holds precisely when U is in this box. Okay, so this is just a D-sided orthogonal range query. So we're going to use ranged-based data structures to solve our problem. And luckily this is known. There's these data structures which can perform queries and deletions in time log n over log n to the d minus 1. And so if you just plug this into our framework, then we immediately obtain that you can compute the largest Pareto-optimal subset in time n to the 1.5 times log n over log n to the d minus 1. Now, as I mentioned earlier in the plane, this can actually be done at n log n time, but as soon as you go to 3 dimensions or even higher, it's not clear how to get something that's near linear. So the fact that the dimension it only appears in the polylog factors is surprising. And so we can get this into the 1.5 result. Let's talk about the second application, which is the largest loose subset of disks. So I'm going to say D is our collection of disks. And remember, I can define the preset where I say D prime is less than D if the disk D is fully contained inside the disk D prime. So a subset is loose if no disk in S contains any other disk in S. Again, this exactly corresponds to an empty chain in the poset I've defined. In the figure below, I've given an example of such a loose subset. So a loose subset corresponds to an empty chain, and in particular, I just want to highlight that you should compare this to the independent set problem, which is known to be NP hard, right? So here the disks are allowed to intersect, but no containment is allowed. And perhaps without the context of anti-chains, you would suspect that computing the largest loose subset is NP hard, right? Just like the corresponding independent set problem. So it's quite surprising that you can find the largest loose subset in polynomial time, whereas the independent set problem is NP hard. Okay, so how do we find the largest loose subset, or equivalently, the largest anti-chain? Well, again, we need to exhibit a data structure that can perform our query operation. So the query operation is given a disk Q, we want to be able to return a disk D such that Q is less than D. In the context of our partially ordered set, this corresponds to finding a disk D such that D is a subset of Q. So the way we implement this data structure is the following. For each disk X, we can define this function delta X, which takes a two-dimensional point and computes the distance between the point and the center of the disk X plus the radius of X. Okay, and so you can actually just check via a bit of algebra that a disk D is contained in a disk Q if and only if delta D of CQ is less than or equal to RQ. So what this means is we want to determine if there is some disk contained inside the disk Q. So what this means is that we should dynamically maintain the following function. For a given two-dimensional point P, we should maintain the minimum of delta dP over all disks D, right? So we can just simply compute f of CQ and check if that result is less than or equal to RQ. Now, dynamically maintaining this function at first may seem a little hard, especially for all points, but it turns out that this just reduces to computing the lower envelope of the following collection of surfaces in R to the 3, right? I can just look at these functions in three-dimensional space. These are x, y, monotone surfaces. And by taking the lower envelope of these surfaces, I get the function f. And this is actually studied by Kaplan et al. In 2017. And they can, in fact, do this dynamically with the update time log n to the 10 plus epsilon, where epsilon is an arbitrarily small parameter. Okay, so just plugging their result into our framework, we can show that the largest loose subset of disks in the plane can be computed in n to the 1.5 log n to the 10 plus epsilon time. So the conclusion here is that this framework we've presented is really useful for computing anti-chains and implicit posets. And in particular, if you've defined the poset correctly, what an anti-chain actually means, corresponds to a very natural geometric problem. There are other similar frameworks, like I mentioned, that kind of exploit this usage of dynamic data structures to speed up existing combinatorial graph algorithms in the geometric setting. And also in the paper, we present a few other results of this framework, which I haven't talked about today, such as the largest subset of non-crossing rectangles, the largest subset of isolated points, and I encourage you to check them out if you're interested. The other question is, we're looking for more applications of this, right? It seems like there could be other natural geometric problems that one is interested in solving, and it turns out they're just exactly corresponding to an anti-chain in some carefully defined poset. And so if you have a data structure which can fit into this framework, then you can solve this geometric problem quite easily. So what other applications are there? And that's it. Thank you for listening.